Okay, so let me probably review this part again. Okay, so we are particularly interested in this case. So we have, let's see. Okay, we are particularly interested in this case is we have this N1 here and N2 here. And this is omega 2. Okay, so this is a case we are particularly interested, okay, to know what's going on, because this is a case we can have wave going up to here and then reflect back and then become kind of evanescent. So wave energy cannot go up. Okay, when it go to here, it will be reflected down. And that's what we're particularly interested. Okay, so the equation, governing equation can be written in two parts. One part is for upper there. Okay, so say this is G equals to H. This is G, and other part is lower there. Okay, for lower there, these two are identical, except here you have W1, 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 and here we have W2 and here N1 here. So we have two equations, N2 square and this square W1, oh sorry, W2, G square equals to 0. Okay. Okay, so okay, now we apply the normal mode method, or method of normal modes, and that means our W prime. So those are primes, 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 primes. Okay, so W prime, okay, equals to W head of G, or G and e to the I, or kx minus omega t. Okay, we substitute into this and then get two identical equations, except we convert them into the Fourier space or Weyl number space. Okay, and that's called the method of normal modes. Okay, so then this will become like that one, d square, one head, dg square, plus m1 square, w1 head equals 0. And here becomes d square w2 head dg square plus m2 square w2 head equals 0. Okay, so here these two on the right hand side. Okay, now m1, okay, square is equal to k square times n square times omega square minus 1. See, this is divided 1 square. Okay, no square here, no square here, no square here, like that. Okay, and actually we can draw together, just say mi, and here we just omega I. Okay, and I represent either 1 or 2. Okay, so we can draw it together. Okay, now what's our solution? Okay, so the solutions, okay, the solutions will be, we have W1 head equals to A e to the I m1 times G minus H, m plus B e to the minus I m1 times G minus H. Okay, that's the lower. Okay, so everybody's copy down this, right? Yes. Upside down. Oh, that's right. That's right. Yeah. Okay. So this is 2. This 2, 2, 2. I'm going to erase it anyway. Okay. So, okay, you just change it in your note. Okay. So here will be W1 prime, W2 prime. These are W1 primes. Okay. Okay, so now we have W2 head equals to C e to the I m2 G minus H plus D e to the minus I m2 G minus H. And in the lower layer is W2 head equals to A e to the I m1 times G minus H plus B e to the minus I m1 G minus H. Okay, now as I said, okay, A, B, C, D are determined by the lower and upper boundary conditions. Okay, so we need lower boundary condition and upper boundary conditions. And then we need 2 interface boundary conditions. Okay, so 2 interface boundary conditions. Okay. Okay, now later we're going to talk about when we have mountain. Then we have the, okay, assuming the boundary layer is very thin and the friction is not important, then flow will be go over the mountain, follow the mountain. Okay, we'll talk about that when we go to the mountain waves. And right now, in general, if you have flat surface, then flow, no matter what you do, you flow coming down this way or going down this way or flat, okay, or slant-wise, you cannot penetrate into the ground. So low boundary condition is W head. Okay, this one. Okay, W1 equals to 0. Okay, because we assume W1 prime equals to 0. Okay, so make the Fourier transform or normal mode and it becomes W1 head equals 0. Okay. And upper boundary conditions, you have 2 types. One type is called radiation boundary condition, which allows the wave energy can propagate to the far infinity. And other type is okay, the boundedness. That means it's bounded. So your solution is not supposed to grow exponentially with height if your source of disturbance is in the lower layer. Okay, so that's upper boundary condition. So here we just say, okay, we just say W head 1 is equals to W head 2 at G equals to H. Okay, and the square W1 head dg is equals to kw square 2 dg at g equals to h. This is not always true. Okay, this is always true. Okay, but this is not always true. Okay, this one you have to derive it. If there's no forcing across the boundary, edge boundary, then that is correct. But if there's a forcing, then you have to integrate, okay, to get that interface boundary condition. Okay, so now we are about ready to do, and now, as I said here, omega 2 is greater than n2, and here, okay, is there, okay, the lower there, omega 1 is less than n1. Okay, so that will give us particular solutions. Okay, so we are particularly interested in this case, number C. Okay, and case A and case B are relatively easier to solve. Okay, and case C is more kind of complicated. So now we are looking at this case. Okay, N2 is less than omega 2. Okay, omega, and omega is less than. Okay, so I shouldn't say this. Omega. Okay, omega less than N1 in the door there. Okay, so now since W1 head equals 0, so that means at low boundary condition, at lower boundary, so that G equals 0. Okay, here. So that means this will be equals to 0. Okay, at G equals 0. Okay, so when G equals 0, where A to the E to the I M1. Okay, G equals 0, so this becomes minus H. Everybody follows me? Yeah? And then second term becomes B, and then E to the, okay, this is 0 again, so negative cancel out. We have I M1 H. Okay, so this means A E to the minus I M1H equals to negative B e to the I M1 times H. Okay. And this means A can be expressed as a function of B and others. Okay. Okay. And that gives us, yeah, that's e to the I, yeah, that's correct, right? Something wrong, Chao? 2I M1, yeah, that's correct, right? Okay, so this is W1. So that means we apply one boundary condition, then, okay, that will reduce the number of coefficients to be 3, because we kind of represent A by B. So that means the solution here can be rewritten as this one. So then we have W1 head equals to, we can pull B out, okay, and write this one first, e to the minus I M1 times EG minus H, and then minus, we have minus here, e to the 2I M1H times e to the I M1 times G mass H. Okay. So everybody follows me? Yeah? Okay, so now this is our solution. This is our solution. Okay, so how many coefficients we have? 3. So now we reduce 4 to 3 because we apply one boundary condition. Okay, once we apply it, we no longer worry about no boundary condition. And the next thing, okay, is determine the upper boundary condition. Okay, so G is greater than H. Okay, so this is positive. This is positive. This is positive. Okay, this is positive. Okay. So, and this term represent, let me see, G minus H, okay, M2, let me see, M2. Okay, so M2 is like this. Okay, so now I think I believe everybody has done with this, right? Yeah. Okay. So now next thing is try to check what's M2. Okay, so M2 square equals to K square times N square divided by omega 2 square minus 1. Okay. And omega is greater than N2, N2 here, omega here. Okay. Omega, you see. I don't think it is correct. Chow. This I is here. Right, I is there. Omega 2. Okay. So omega 2 is greater than omega N2. Okay. So this omega is greater than N2. So this means this is more than 1. Okay. So this will become negative. Okay. So M2 square can be written as negative K square times 1 minus N2 square divided by omega 2. Okay. If you like, you can write omega 2. Okay. But I just tired of writing it. So, but you know what I meant. Omega square here. Okay. And this will be positive. Okay. It's negative. That means M2 will be real number or imaginary number. Will be real number or imaginary. Imaginary. Okay, will be imaginary. So M2 will be imaginary. Okay, not real. Okay, because this is positive, this is negative. So you take square root of negative value, that is imaginary. Okay, so that means M2 can be written as I N2. Okay, and N is real number. Okay, M is imaginary. Okay, that's why we're N here. Okay, so this means M2 equals to negative. Okay, so M2 is equals to I times N. N2. M2 is equals to I N2. Okay, understand? Agree? Do you all follow me? Follow me. Smile, smile. Okay, please. Yeah. Yeah. Do you follow me? Yeah. Any questions? Yeah. Are you okay? Yeah. Okay. 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 So now, if Okay, I'm going to erase it quickly. Okay, so copy down quickly. Okay, because it's so easy to copy down. So you have I n2 times I, that is what? Negative n2. Right. Okay, so I'm going to erase it now. This will become minus n2. Okay. And this I n2 times I, we replace this m2 equals to I n2. Okay, n2 is real number. Okay, m2 is imaginary number. So this I times I is negative. Negative, cancel this negative out. So this becomes n2 and then times g minus h. Okay. Okay, so can somebody tell me for this solution here, just ignore the lower part, just upper there. The wave is not going to increase, okay, exponentially. That's called boundedness condition. Boundedness, okay, condition. Okay, that means this growing one, okay, and this go like this, okay, decay quickly, exponentially. This is unphysical. Okay, understand? So if that is gone, then we have solution like this. In the upper layer, we have solution like this in lower layer. Okay. So then, how many coefficients are left to solve? For us to solve, how many? 2. Which 2? C and B. Okay. And then C and B will be determined by the interface boundary condition. Okay. Okay, so everybody copy down. I'm going to erase it. Okay. Okay, I guess I can erase this. Okay. I'm going to erase it, okay. So this is unphysical, so we take it away. Okay, so we apply the upper boundary condition, which is boundedness condition. Okay, so and we have this one. So now we have solutions controlled, governed by these two equations. And in order to solve the problem, we need C and B to be solved. And they are kind of have to be solved by the interface boundary condition. Okay. And so that is W1 equals to W2 and partial square W1 partial G supposed to be equal. Okay. And this one is called kinetic boundary condition. And this is called dynamic boundary condition. Okay. And now if you let G equals to 0, no, G equals to H, okay, then we can solve it quickly. So now at G equals to H, then W2 equals to what? C e to the what? G equals to H equals to 0. E to the 0 is 1. So W1 head has to be equals to W2 head. That means C equals to P times 1 minus e to the 2I MIH. Okay, agree? No problem, right? So this means we can substitute C into here. So that gives us P times 1 minus e to the 2I M1H times e to the minus N2 G minus H. Okay. Agree? Okay, so I'm going to erase it here. So the upper layer has a solution like this. W2 head like that. Okay, we applied this already, this bunch condition, interface bunch condition already. Okay, and then lower there, okay, we still have this, okay, this solution. So now how many coefficients are left? Only one. So that one will be determined by the other interface, second interface bunch condition by this one. Okay, so I think it's pretty easy. Okay, you can do that. I'm not going to spend too much time on that. Okay, but just give you kind of step by step to a certain point. But then that becomes complicated, but shouldn't be difficult to do. Okay, so then now, wow. Okay, so real number. Okay, so the kinetic bunch condition requires, okay, is V1 dot N1 equals to V2 dot N2. Okay, that's called a general bunch condition. Okay, we already talk about it, right? Okay, this interface bunch condition, okay, that kinetic bunch condition. So let me go it quickly. Why we have this bunch condition? Okay, in general, you have that kind of bunch condition. Okay. So what's V1? What's V1? Total velocity in which direction? How many dimensions do we have now? 2. We have x and g. Okay, we have x and g. So V1 is equals to what? This, okay, this vector is equals to what? U. And V2 is this second layer. Okay, upper layer is V2. And N2, okay, so N, let me see, N1 here, this is, okay, this is N1, this is N2, okay, and then that's in vertical direction, so then you have W times N1 equals to W times N2, dot N2, okay. and then that gives us W1 equals to W2. That gives us, okay, so that gives us W1 equals to W2, okay, prime. And then you make the transformation into the Euler number space. That gives us this W1 head equals to W2 head. Okay, understand? Okay, so that's a general kinetic boundary condition. Okay. So N1, Ni is a vector. Okay, so that's a vector. Okay. So if N1 is equals to the perpendicular to the boundary, right? Perpendicular boundary. So what N1 will be? What N1 could be? What's N1? Unit vector perpendicular to the boundary, and that boundary is horizontal, right? The boundary horizontal. So what's N1? K. Okay, that's K. So N1 is K. Okay. How about N2? Perpendicular to the boundary. Because the boundary is horizontal, right? The boundary horizontal. So that is also K. Okay. So now everybody follows me? Yeah. We try to apply this here and read it carefully here. N1 or N2 are this times this. That is W1. Okay. And how about V2? That N2. Okay. That would be W2 prime. Okay. So these two has to be equal. So that's why we say W1 prime equals to W prime. And then we transform into wave number space or Fourier space in general, then becomes W1 head equals to W2 head. Okay, so we have that, okay, the boundary condition here. So just give you one extra explanation. You need this kind of understanding to get into more theories to understand it, okay. Okay, so then we have W1 prime equals to W prime. Okay. And other boundary condition is called dynamic boundary condition. This is called kinetic boundary condition. Okay. And that is basically, it is the pressure has to be continuous. Okay. First one, kinetic boundary condition means your motion has to be equal. That's okay, perpendicular to the interface. So that's W1 equals to W2 primes. And then dynamic boundary condition is pressure has to be equal. Okay, at that interface, okay, on top and below, okay, that to be equal. That's called, okay, the pressure got to be equal. And that can be derived, you can derive to be there, like this. Okay. I'm not going to do everything for you, okay, so I let you do it. Okay, yeah, Chang help me to keep note. That is one of the next, okay, homework problems. Okay, good. So, okay, and then you can easily apply that to get the solution. This is a solution, like this. Okay, and then apply the dynamic boundary condition. We'll get into this. Okay, and then once you have that, then you can get the eigenvalues, okay, and eigenfunctions. Okay, so this is also called the eigenvalues, okay, omega and k, okay, and then eigenfunctions, and we get this W1 equals like this, okay. Okay, so maybe I should take a break. We should take a break, or you want to continue? Take a break. Okay, take a break. Okay, yeah. Okay, so we take a 10-minute break. Okay, thanks. Okay, so now let's continue. Remember when you apply W1 head equals to W2 head, okay, then we get this. So it's up to you. You wanted to use C in terms of B, or use B in terms of C. You just move this to the left side. Okay, over there, okay, apparently we keep C, okay, and then so B will be a function of C, and then you substitute. So then instead of B here, we have C here, we have C here, okay, but it's same meaning. Okay, so now in the door there, W1 head will be equals to that C times this, and then e to the I m1 g minus h, e to the minus I m1 g minus h. Okay, that's the solution in the door there. Okay. Okay, so I guess I can erase this. Okay, later when we come to discuss about the mountain waves, we'll talk about more details. How do you determine what's a wave going up, what's a wave energy goes down, okay? And they are represented by these two terms, okay? So in general, if you have e to the I alpha, okay, and then e to the minus I alpha, okay, the alpha is a real number and positive, okay, alpha is a real number and positive. Then this term represents upward propagating wave of the energy, and this one represents downward, okay. Right now you don't understand, that's okay, okay, just take it, because later we're going to discuss it when we talk about mountain wave. Okay, so now talk about these two. Can somebody tell me which one represents upward propagating wave, which one downward? Just look at I M1, this, okay, I M1 of this, okay. Remember M1 is real number. Okay, so which one is upward propagating wave? Which one downward? I'm talking about energy. Which one? This one is upward. Why? Because G is less than H. So this is negative. So this is positive. Okay, so this becomes positive. So that is upward, this downward. Okay, so okay, so here we have a solution like that. Okay, so here we have solution W1 equals to, okay, e to the I m1 times g minus h. Okay, plus e to the minus I m1 times g minus h. But since g is less than h, okay, so this one representing upward propagating wave, this one downward. Okay. Okay. So, and now since we have the everything here, so let's say if we call it what did we call it? In the beginning we call it ABCD, right? So in the beginning we call it ABCD. See here, okay. So this is low layer, right? Low layer here, and this low layer here, A, B, right? So this term is term A, right? This term B. So term A representing the downward propagating wave, and term B represent upward propagating wave. When I say propagation, I mean the energy propagation. Okay. So if I come up with a ratio, say R equals to term A divided by term B. Okay, assuming this is our energy source, say like a mountain is our energy source. Okay, then you have wave generated by mountain propagate upward and then reflect down. Then term A minus term B divided by term B is what? It's the part of the energy reflected by the interface boundary. Okay, it's generated by the mountain and then go up and then reflect down, and that reflect down is this term A, and then this is generated up, okay, divided by this term B. This is the reflection coefficient. If it is half, that means half of the energy generated, it will be reflected by the interface boundary. Okay, so that in that way you can calculate how much of the energy being reflected down. Okay. Okay, so that equation, that solution is very useful. Okay, so we talk about, when you have basic flow like this, it's G, okay, and here we have N1, N2 here, like that, okay. And then if omega is here, in between N1 and N2, then all energy produced, generated by the low layer disturbance, like a mountain, okay, will be reflected back. Okay. And here we also assume our U is uniform. Okay. But you can have other case. If your N is constant, your U changes with height. You also can have reflection. You can also have reflection. Okay. Okay. You can also have reflection too. So not only you can vary N, you can also vary the U. okay, or combination of U and N, then like this case. Okay, okay, you can have, okay, this is temperature profile. Okay, that will give you N, okay, and this omega, okay, and then you can also have more complicated case, okay, except, okay, then this case. So you can have your N is varying with height smoothly like this, okay, your omega is like this. Then when your omega less than N, this there, okay, will be, well, kind of trapped in this there, okay, because here N is less than omega, and here N is less than omega. That means they are evanescent, okay, and here N is greater than omega. That means your buoyancy force is more important. That means the wave can propagate up and down or down, okay, or up and down. So then wave generated in this layer can go up, can go down, okay, so wave will be trapped like this, okay. So this board, okay, this board error means wave energy. So this wave energy is going propagate this way, this way, this way, and then bump into reflection level, and then reflect down, and then go like this, and then bump into the lower, okay, boundary, interface boundary, and then reflect back. So they can go back and forth in between this. Okay, so this second layer is able to trap the wave. We call wave trapping. Wave generated will be go up to here, reflect back like this. Okay, and okay, so this is good velocity. What's this? What's that? That's the particle motion. Remember? Okay, we talk about that in basic wave dynamics. Okay. This represent the particle motion is, okay, go this way. And what's this? What's this error? Phase velocity. Okay. And phase velocity is perpendicular to the group velocity. And group velocity carries the energy with it. Okay. Okay, I guess we are done with the reflection level. Okay. Let me see. Oh, we still have some here. Okay, so so if we consider two-dimensional linear non-rotating inviscid homogeneous system, okay, governed by 3.5.1 to 3.5.4, then we can reduce to this equation, and m squared is equals to n squared divided by u minus c squared minus ugg divided by u minus c minus k squared. C is omega divided by k. Okay, C is omega divided by k. Okay, remember, okay, omega divided by k. You may wonder why omega divided by k is equals to c. Okay, you may wonder about that. Okay, omega is equals to 2 pi. I'm talking about angular. Okay, angular frequency. Okay, if it's not angular frequency, we just said generally the frequency will be 1 divided by the t. What's t? Wave period. Okay, And then k will be 2 pi divided by wavelength. Right. So you do this, this becomes what? Becomes L divided by T. So L is a distance divided by period, a time. What's that? Speed. Okay, that's okay. So that's why we call this phase speed or phase velocity. Okay, like that. C omega. So if we assume U in general is not uniform, it can be vary with height, and N can vary with height, then this is a general Cosine, Taylor-Cosine equation. Okay, Cosine equation. And this m squared will be more complicated. Before like this, we only have this. We only have this. Okay, we only have this. Okay, before we only have this. So if there's no shear, vertical shear I'm talking about. Okay, then m squared of G is equals to n squared divided by U minus C squared minus K squared. Okay, because UGG is equal to 0. Okay, and this equals to n squared divided by U minus C. C is what? Omega divided by K squared minus K squared. Okay, so what it is? It's n squared divided by, we have divided by K squared, and then we have UK minus omega squared. Okay, and then minus K squared. Okay, this will give us K squared times n squared, and then that gives us omega minus KU squared minus K squared. What's this? Capital omega squared. Okay, and K squared, n squared minus K squared. That gives us what? Give us n squared divided by omega squared minus 1 times K squared. That's what we had before. Okay, so you can write this way. And then when we have the vertical wind shear, then we can add this term into it. Okay, we just write it in a different way. Okay, and this is called the Taylor-Cosine equation. Okay. So that means your U can come into play if you have wind shear. Okay, so when you do a situation, your U not necessary to be constant, not uniform with height. So your U changes and N changes. Okay, come into there, and you can use that to determine your M squared to be positive or negative. If positive, that means M will be real number. If negative, that means M will be imaginary number. Okay, and then they have two different type of solutions. One is vertically propagating wave region. Other one is evanescent. Okay, and then you can determine where you have the reflection level. Okay, you can use that. That's a general case. Okay, and you also can reduce the form in the real number space of the Taylor-Cosine equation. It's in physical space. It's like this, more complicated. Okay, and it's not really that complicated because if no vertical wind shear, this will be 0, and this will be d squared w prime, the x squared plus d squared w prime, the g squared. Okay. Okay, so that will help you determine the wave reflection level. Sometimes you probably have more than one reflection level. Okay. And Later we are going to learn about D waves, okay, because of this reflection. Okay, you have a stable layer, n square, okay. N1 square is greater than N2 square, much greater. Then you can have wave trapped in the lower layer. That's because the wave energy produced by mountain is going to go up to that level, being reflected down, okay, a lot, and then you got wave trapped. That's called D waves. Later we're going to talk about it. So you need this background in order to understand better of the D waves. And also you can also trace, use a path or race to trace it, like 3.12, okay. Like 3.12, you can trace the, it's called path or race, okay. You can trace the wave energy, where does it go, where does it reflect back. Okay, so we are done, but keep this in mind, okay. This is a more general case. Not only U is called constant, U can change with, okay, speed, with height. So keep this in mind, okay. Then, okay, so if we write our wave equation, the Taylor-Goldstein's equation, like that. And as I said, depending upon m square is positive or negative. Okay, if positive, then you have the vertically propagating wave regime. If it's negative, m become imaginary. Then, okay, if your boundary condition is assumed is bounded, then it's going to be evanescent flow regime. Okay, so keep that in mind. So you can determine that. Okay, but when you look at that, okay, there's one very special level. If it happens, the wave characteristics, okay, wave properties will be totally different. Okay, that is when you have U equals to C. Okay, that's a big problem because mathematically that's called critical. Okay, a critical problem. Okay, and so that gives us a level of very strange, give us very unusual wave behavior. And that's the next thing we want to talk about. It's called the critical level. If this U is equals to wave propagation speed, okay, then we enter into a very strange solution because in normal way we cannot solve it. We have to use very special technique mathematically to solve it. And that's the next topic. And that's called critical level. Okay. And that's also very important phenomena, beside the diffusion level. Okay, so now if U equals to C, we have a singularity. Okay, mathematically. Okay, and that level we call it G sub C, and we call it critical level. If G, okay, G equals to G sub C, okay, at that level, if we have U equals to C, then it's called the critical level. Okay. We probably don't have time to go over into details, but at least I give you the general concept. What is critical level? What's behavior? Okay, that's very important. Okay, so sometimes if you bump into some situation in that, like when you do modeling, okay, sometimes you find very strange behavior, and if you don't have the background in this kind of dynamics, it's very difficult to explain, okay, the phenomena. Okay, so when we have C, U equals C, okay, we have a singularity mathematically, and in physically, we call it critical level, okay, very strange behavior, very unusual behavior. Okay, so say we have a thunderstorm like this. Okay, there it is. And air here, it kind of comes in, go like this. No, go like this, and then also go like this. Okay. So when you look at here, when you look at here, then your basic flow will be, you have flow go like this. No, probably just object, right? Okay, this go this way, and yeah, go like this. Okay, so here critical level. Okay, if just imagine like if I have a score line, okay, propagating this way, and then where basic flow all go this way, but at a certain level they are equal. Then that give us the critical level. And critical level also very important related to the diabatic heating problem like thunderstorms, because when you're critical level, that means at that level is almost stagnant if you are following the storm. Okay, following the system. That level, your basic flow is almost equal to 0. Okay, and that's important. Why? Because when you have, when you say you have flow blowing and you try to hit it, okay, part of the energy, okay, heat energy, the heat is part of energy. Okay, that heat will be carried advected out. So your heating effect is not very strong. Okay, and heating effect very strong is when you have quiescent fluid. There's no wind, and then that all heating will coming out to induce vertical motion, okay, and bring air up, okay. But okay, when you have wind shear, okay, that okay can be tilted, and so it's okay, so it's going to be not very effective. Okay, at the critical level that you have very efficient heating. That's why it's so important. Okay, like this one is the mean relative score lines, score line with the critical level here. Okay, see here, flow comes in and then we come back. That's almost like this part. Okay, and then another part is coming in, go like this way. Okay, and then you have the critical level here. Okay. Because this is observed following storm moving reference of frame. Okay, frame of reference. Okay, other important application is this. Important application is this when you flow over mountain, and you got wave generated, and this wave, okay, can steepen, can overturns. Once you overturns, this is this level. Okay, this is your U, right? This is your U. Okay, and okay, this is your U. Okay, your U is generally toward right. By this point, your U is equal to 0. right? Overturns is equal to 0. So your u equals 0. Okay, is that u equals 0. And that u equals 0 level for that mountain wave case is critical level. It's critical level. Why? Because when you have the mountain wave, and assuming the steady state mountain wave, when you have the steady state mountain wave, what is C? What is C?
Only the x direction.
No, I'm trying to find critical level. In general, critical level is u equals to c, right? Okay, but here I say when u equals 0 in this steady state mountain wave case, it is critical level. U equals 0 is critical level. It's because c equals 0. Okay, for steady state. Why? Because steady state means what? Partial t equals to 0. And what's partial t? That's I omega equals 0, right? Right. This means omega equals 0. Okay. And C is divided by K is 0. Okay. So that means for steady state mountain waves, okay, U equals to C is equals to 0. That's the critical level. Okay. And this is very important because once you have critical level like this, and then the wave behavior is very different from the normal case. That means in normal case, there's no critical level. Okay. And we're going to talk about that later on. Okay. But right now, you need a background to build up. So when I explain that in the mountain wave theory, then you can, oh, okay, that's what we got. Okay. Earlier we talked about. And this kind of critical level is not associated with the basic wind. The basic wind in general is from west to east, this way. Okay, and this one is induced by the mountain wave. So it's called wave-induced critical level. Critical level, okay. So we'll talk about that later on, but right now I'm going to talk about what's the general property of the critical level. Oh, one warning. Thread. Okay, what is thread? Okay, not warning. I think probably should be 警告. Okay, yeah. Right. Warning is 警告. Okay, this threat is somebody going to kill you. Okay. Okay. So see here, this is from Lin and Wang. Wang is Wang Tinan. Okay, he's in Kechibu right now. He was my PhD student. He graduated from NC State. We published his paper in 1996 in JAS. And so you can see here. You can see here. Okay, under certain conditions, the flow come in. You don't have here, but here you can see. Okay, not very clearly, but here you can see clearly. See here, it overturns. Okay, it overturns, and that level is called critical level for mountain waves, steady state mountain waves. Okay, only for steady state, C equals 0. Okay, because omega equals 0. Okay, so in order to solve the solution near the critical level, because it's singularity, so you need to apply special technique, the asymptotic solution approach method. And this asymptotic method, like for example, you can use the WKPJ method, okay, and you can approach and solve the solution approximately, okay, asymptotically. Okay, doing that. I'm not going into details because it's more advanced material, okay. But you can do it in the papers, okay. You can do it the book in 2007, and then you need more advanced. You can go to the the papers referred in the book, okay. So when you have dg dt, that's proportional to G minus G sub C. That's the critical level square. Okay. Okay. So when you apply the WKPJ method, you find this dt dt is proportional to G minus G sub C square. Okay. When G is approaching the critical level, like that. Okay, that gives us T minus T0. Okay, will be proportional to 1 minus 1 over G minus G sub C. Okay, but since G is approaching G sub C, downstairs, the denominator is almost very small, approach 0. So what does it mean? This means it's become very large because G minus G sub C is very small. You approach it, okay, and that means the time it takes to reach critical level will be very large. And once you reach it, it takes infinity time to reach it. Okay, so in other words, okay, your wave energy, okay, cannot, okay, when you take infinite time to reach the critical level, okay, it takes forever to reach the critical level. Okay, so where does energy go? It's not reflect back. So the critical level is very different from the reflection level. Reflection level is your energy goes to that level, reflect back. But here, where energy takes forever to get there, eventually absorbed by that level. Okay, that's very different behavior. Okay, as I said here, physically it's absorbed by the critical level. Okay, instead of being transmitted. Okay, normally you only have 3 ways, right? You have only 2 ways. One is reflect back, that's reflection level, or transmitted. Part of energy transmitted, part of the energy reflected. But this one is special. It's been absorbed. Okay, because where energy will keep going, but take forever, and physically that means the energy is gonna be absorbed. And sometimes you hear people talking about critical layer because, because here U is equals to C, okay, but C is omega divided by K. So if you have only one wave with constant K, then you only have one level. But in general, your wave could be very complicated. That is equals to you have long waves plus shorter waves plus shorter and shorter waves. Okay, many waves. Okay, so each one has different K, and then so each one has a different critical level. Okay, all together, then you got many critical levels, and that whole layer is called critical layer. Okay, so in reality, it's critical layer. Okay, because In reality, you don't have one single wave with only one k. So now, you see the difference? What's this? The group velocity. Group velocity, you go, you don't bounce back. You go, eventually become parallel to the critical level, and absorbed, energy absorbed. You don't reflect back or penetrate, transmit it to upper layer. Okay. And this is your basic wind. Has a wind shear, and this is your wave propagate at this speed. Okay. So your wave propagate this speed here. Okay, and that equals to U of G, and this level is called critical level. Okay, and wave behavior is very interesting. Okay, I guess I probably will not go into details, but just kind of summarize. Okay, what do we have? Okay, so if we apply U, equals to C plus U, C prime, because this C is equals to U, right? At the critical level. So, but you have small, you use the Taylor series expansion, like that, and N2. Okay, N equals to N at critical level plus N C prime, because N is functional height, and then times this, and times this. Okay, and then you can substitute into the equation, and then take the and then you assume the series, solution, for differentiation, and then eventually you become alpha squared minus alpha plus alpha sub I. C equals to 0. Okay, this is the critical level. Okay, and I is N divided by U. Okay, and that is called the Richardson number. Okay, I is called Richardson number. Okay. And you solve this, that's in differential equations. Okay, then that's called integer equation. And you can solve alpha, and that equals to like this. Okay, and 1/2 plus minus I times mu, and mu is equal to square root of Ri minus 1/4. Okay, and then you can find a solution in this form. Okay. Yeah, based on the WKPJ method. Okay, and this can be expanded into this way. Okay, maybe I should stop here, and let's continue this afternoon and wrap this up. Okay, so then we can get on to the mountain waves. Maybe this afternoon we should talk about the project 1. Okay, project 1. Okay, so I got a chance to take a look at the project 1. Sean already sent you the model. And then take a look, and we can discuss what you need, and can you able to run it, and are you able to do you need to can you plot it? Okay, yeah. Okay, so let's stop here and have lunch. Okay, have a break. Thanks. Okay, so the idea here is, by the way, I should make a more clear description of explanation of that thunderstorm system. Okay, so when your flow coming in, go out like this, and normally if you make the observations with the moving frame of reference, then this observed system is following the C Okay, so when U is reversed, that's the critical level. Okay, remember, the critical level is U minus C equals 0. But if you follow C, then if U reversed, that's the critical level. Okay, so if you take a look at here, then you look at the only U component. Okay, only U component. Then here, wind from east. So then it's supposed to be like probably like this. No, wind go like this. Okay, and this is U equals 0. But since we are following the C, okay, so then this is critical level. Okay, and so that's I think that's what it means. Okay, now next thing is when we have if I got this. Okay, so say if you like this, U or G, and you have say you have a kind of N of G like this. Okay, just for example. And if the system, the wave, or over there, that the other one is, you're assuming that the convection system is like a wave. Okay, then propagation speed will be is the phase velocity. Okay, so here if this is C, then you find then this will be C. Okay. Then this will be critical level. Critical level. Okay. And so then if you are going with so say if in the moving frame, then you see wind go this way. Wind go this way. Okay, at the critical level. Okay, and so then you see like that. This is critical level. Okay, if you follow the system. Okay, right. So that's a moving frame like you learned from general physics. Okay, so now how do you solve the problem? The problem is so now this is critical level. That's this is height of G sub C. So then near in the vicinity of G sub C, the critical level, then you make U of G, you do the Taylor series expansion. Okay, just like F of X. Okay, then what you do is you have F of X0, right, plus df dx, right? Okay, and then x minus x naught. Okay, or simply say you will be a prime, of x naught, right? Okay, and then plus 1/2 f double prime or x naught, x minus x0, and then plus more. Okay, so U will be U, at GC, that's the central point. Okay, and then you have du, dg, and then at the GC, and then G minus GC. Okay, and then plus 1/2 the square U, dg square, G minus GC square plus this. Okay, So say we ignore this. We just pick up this part. Just approximately equals to that. Okay. Then okay. Then U of G will be approximately equals to U at GC plus UG and G minus GC. But what's this? The velocity here, that's equals to C, right? So this becomes U of G equals to, equals to C plus UG and G minus GC. Okay, that's what it has here. Okay, C means it's evaluated at critical level. Just like here, you evaluate at S naught, you evaluate at GC, like this. Okay. And then you do same thing for N of G. N of G equals to NC. NC is N at GC. Okay. Plus, okay, NC prime. Okay. Here you can say prime 2. You can say prime 2. You want. Okay. C prime. Okay. And then G minus GC. So then you substitute into the equation. Okay. Then you can try to solve it using the WKBG method. Okay. And then you substitute, you get this initial equation. Alpha square minus alpha plus RIC, okay, and this one probably, because I is supposed to be equals to N square and UG square, right? Yeah, U square. So that may be not quite right. Oh, that's okay. Yeah, N square. So it's N at C, G at G prime at C square. So this is correct. Okay, it's correct. Okay, so now once you have this initial equation, then we can solve it. We can solve it. Right, we can solve it. It's pretty simple. Okay, so you have the initial equation minus alpha plus RIC equals to 0. Okay. Then alpha will be what? Equals to what? Alpha will be equal to what? Okay. So you have ax squared plus bx plus c. So x is equals to what? Huh? Say it. Yeah, say it. No, say it in English. Yeah, try it. Yeah. Anybody? 2a 分之负 b。No, come here. Yeah, right down. Yeah, you should try to say in English. Okay. Okay, good. Okay. So it's okay, in English you say, okay, negative b plus minus square root b squared minus 4ac, right? And then this one normally we say over. Okay, this we say over. Yeah, over 2a. Okay, yeah. So here your a is 1, right? So it's 2 minus b, that's 1, right? Right, minus b, 1, and then plus minus square root of b squared. B squared will be 1, right? okay, minus 4AC, minus 4 RIC, okay. And then this will become 1/2 plus minus, okay. And then we have 1/4 minus RIC, okay. And then this equals to 1/2 plus minus I square root RIC minus 1/4, like that. Okay. And then we define this as mu. Like this, mu. Okay, this is called mu. Mu. Okay, mu. So we have that. That's what we have. Okay, so near G equals to GC, okay, close to the critical level, then we can with a series solution, okay, we can find this. Okay, so, and this is pretty standard, okay, the differential equation solution, okay. And then after this, okay, then you can expand this as this, okay. And this is argument, okay. Argument means G greater than GC, that will be positive, and then G minus GC negative, that will be negative, okay, 1. Okay, so it becomes this solution. And so then you define argument equals, argument equals to 0 if G greater than GC, okay. Yeah. Okay, anyway, so once you do it, you get a solution here, like this and this. Okay, solution is for G greater than GC. Okay, for G greater than GC. Okay, I think this is for term A, this is for term B. That's these two, term A and term B. Okay, there are two terms there. Okay. And plus means for G greater than G sub C, above the critical level. Okay. And I'm probably not going into detail of this, okay, but then once you substitute into it, then you get this solution, okay. And WA and WB, this is below, okay. This is this is critical level, GC, okay. Above we have WA, okay, plus, and then plus WB, plus, and you have two terms, and below you have WA minus plus WB minus, like that. Okay, remember here we have two terms. We have term A and term B. We just write it separately, okay, because they are plus. Okay, so this is W hat plus and W hat B plus. Okay, so there are two terms. One is above the critical level, and below. Okay, so 2 terms on top, 2 terms below. Okay, so now if you compare these 2 terms, okay, WA plus over WA minus. Okay, in English you say this is absolute value of WA plus over WA minus. Okay, and that will be equals to like this. Okay, and W hat B plus over W hat B minus is equals to exponent. Okay, mu times pi, and then sine UC. Sine UC means if UC is positive, then it's 1. If negative, negative 1. Okay. Okay, so now, okay, we compare this term to this term. So WA hat plus WA minus hat. That's equals to e to the minus mu times pi, and then sine of UC prime. Okay, so let's assume UC prime is positive. Just assume it. You can do that for negative, but same argument. Okay, shouldn't be a problem. That means you have shear like this, increase with height. Okay, so this, okay, this U of G, U of G. Okay, this means U. Okay, so say this is GC. So then your, okay, UC plus is positive. Okay, because it increased with height, the shear. Okay, understand? Okay, this is GC. Okay, so that's, and then other term, WB hat plus divided by WB hat minus equals to e to the mu times pi, and then sine of UC prime. Okay, since we assume this, so that gives us a sine of UC prime to be positive. Okay, so, to be equals to 1. So this guy will be equals to 1. This will be equals to 1. So we don't worry about it, it's 1. Okay, so in other words, then this will be equals to e to the minus mu pi. Okay, and this will be equals to e to the mu times pi. Okay, so A term has different meaning from B term, physical meaning. Okay, so now if say this is critical level, it says disturbance, for example, if disturbance is like a mountain like here, so A term from WA to WA minus plus, you go from here to here, disturbance is going to increase or decrease with height when you go from lower layer to upper level. Upper layer, it's increase or decrease? Decrease. Okay, decrease. So if I have disturbance from lower level, so then if I have disturbance here, this will be decrease. And for B term will be exponentially growing or increase. So you have disturbance like this, and it will be increase exponentially. And if the disturbance is from below, which one is physical? This one. This one physical. This one is not. Okay, because it's increase There's no reason you increase with that. Okay, the amplitude of a disturbance or a wave is going to increase. Okay, when you have the instability, you can increase, or you have heating. Okay, so say here we don't have heating, we don't have instability. Then naturally we will choose this one. This is unphysical because it increases exponentially. Okay. Yeah. So then what do we do? If disturbance is from below, this is unphysical. We knock out this term. We choose 8 terms. They'll be similar to what we had before. Okay. Remember, we have choice when our m squared is negative and m is imaginary. Then we have evanescent flow, and then we have also 2 solutions. One is exponential growing with height. Other one with time. Okay. Other one is exponential decaying. Okay, with height. Then we choose the one decaying. So we choose this one. Okay, very similar to what we did before. Okay. So then we choose that. So then that's also explains because when a disturbance, and then across the critical level, it decreases. Okay, but it's not reflection. It's not a reflection. Wave doesn't reflect back here. It's just absorbed, energy absorbed by this critical level. Okay. Yeah. And assuming Richard's number is greater than 1/4. Okay. Remember I moved that. Remember I have this one. Richard's number. Assuming Richard's number is greater than 1/4. What happens if Richard's number is less than 1/4? Where instability? Where shear instability? When Richard's number is less than 1/4. Remember that? Have you heard? Okay. And so here we are talking about there's no initial instability, there's no instability, shear instability. So Richard's number is greater than 1/4 in this case. So then the wave energy is absorbed. So we choose the atom. Okay. We choose the atom. And then once you choose that atom, then you have that A, you have determined, that is determined by the low boundary condition. Okay. And then you solve it. So once you have the low boundary condition, you know that, like a mountain, then you impose the low boundary condition. Then you can solve that problem. Okay, you find A, because it dropped B. Okay, so that's based on WKBJ, okay, a linear approach. And something I have to caution you is linear theories are not quite accurate in the vicinity near the critical level. So you have to be careful about that, okay. So it's kind of the solution depends on Richard's number, okay. If Richard's number is large, then this kind of argument, the KPJ approach, is not very accurate, but it is close enough. Okay. And so Britain, he used the numerical model in 1971 to study different flow regimes, and he found the following. For Richard's number greater than 2.0, that's pretty stable. Okay. Your shear is not very strong. Shear is kind of weak. The interaction between the incident wave That's here, instant wave from below to the critical level. And the mean flow is largely similar to that predicted by linear theory. Okay. And very little of the instant wave energy penetrated through the critical level. In other words, all the wave energy come to here is absorbed by the critical level, and very small amount penetrate through the critical level to upper layer. Okay, that's Research number greater than 2. If this number is greater than quarter, 0.25, less than 2, then a significant amount of wave energy is reflected. Then a lot of them reflected. That is when this number is small. Okay, then a significant reflected. So when we say the critical level can absorb the wave energy, we are talking about large Research number. Once the Research number become smaller, that means the shear that can come into play. The vertical wind shear that can come into play, interact with the wave disturbance. And so a significant amount of energy will reflect back. Okay. And some wave energy is also transmitted through the critical level. For Research number less than quarter, wave over reflection is predicted. So, in other words, if this number here, very strong wind shear can have the instability. You just need something to trigger it. It's no guarantee you have instability, but when this number is less than quarter, okay, that means that flow could have instability, but you have to trigger it. Okay, so you have a wave generated and then kind of impinge, okay, into, okay, the critical level. Then you can have reflection back, and one thing very interesting is this reflected back of the wave, the energy could be larger than the inertial one. Okay, so that's called over reflection. And that's because you have the shear instability being triggered, and then you kind of triggered, you release, okay, the energy from the basic flow. To understand this, I just try to give you an example. That's about instability, like shear instability. For example, if you drive on highway, okay, you drive on highway, okay. So say here's Taipei, okay. And so say here is okay, Thailand. And normally highway has a medium. It's called medium. Okay, it's called median. Okay, it's okay. So separate. Okay, the one going to north and the one go to south. So you have median here, and then car go this way, car go this way. Okay. And this is here, right? Okay. But you don't trigger it, it's okay. Even it's going very fast, okay. Okay, going to north, going to south. However, if somebody is tuku, okay, driving tuku, and then bump into the median, and then bump into the other side of the highway, then you release the instability, you release the energy, okay. That's shear instability, okay. So when you have strong shear, it's not guaranteed. For this number less than quarter, normally people know that, okay, you have potentially, you can have instability, but you have to trigger it, okay. So now if we have a critical level, and then we have wave impinge on it, and then you can have over reflection because you extract energy from the shear, okay, from basic flow. Okay, that's called wave over diffraction. And how many of you know about instability? How many of you have studied instability or heard of instability or learned instability? Huh? You have, right? From 大洞, right? Yeah. How about 小洞? Okay. You learned from 大洞. Anybody learned from 小洞? Okay. Yeah. So, okay, from 大洞you learned instability. Instability grow by exponentially, right? By instability by like maybe alpha t or something, right? Exponentially. Have you thought about it? Why instability has to grow exponentially? Okay. Why? Why not? Why not go like this? Why not go like okay? Like for example, why not go like with this t, right? Why not go with like t squared? Why not go with t third? Why not go with t 1.5? Why have to go to exponentially? Okay, one theory by Lincoln at MIT. He used to be at Harvard. Okay, one theory is, okay, when you have wave coming into here, you got reflection back. If reflection is in phase with incident wave, then you got exponential growing. That's called normal mode. Normal mode. Okay, that's called normal mode. Remember, we talk about the normal mode method of normal mode. We assume like a W, okay, equals to a W head, right, of G e to the I of kx minus omega t. Okay, that's called normal mode, growing exponentially. Okay, why you have to assume this? Why not assume, okay, t squared or something? Okay, and if something like a t squared or t something not exponentially growing but still growing, that's called algebraic mode. Okay, and so when you have wave reflection in phase with incident wave, then it's growing exponentially. That's called, okay, that reflected wave in phase. If not in phase, then it's going to grow algebraically instead of exponentially. You could grow by, okay, t squared or t to the half or t to the third. Okay, that's called algebraic mode. Okay. Well, and I'm not going to talk too much about that because that is more instability theory. Okay, so you can have the algebraic mode instability instead of normal mode. This is exponentially growing. This is like t to square, t to third, or t to 1/2, that type. That's called algebraic mode. Growing slower than the normal mode. And that's because of reflection. Okay. Reflection is not completely in phase, then some of the energy will be kind of dissipated. Okay. And so only part of it grows, but not grow as large as the normal mode. So, for example, this is kind of stable atmosphere. Okay, like in 1987, I have a theory. Okay, I kind of published a theory for. So, say you put heat in here, and you have critical level here, and you can see disturbance suddenly decays quickly. Okay, energy is not reflected because Reynolds number here is large. Okay, this number here for A is 10, very large. For B is 1. Okay, so you can see the wave can penetrate to the upper layer. Okay, but a lot of them still reflect back. So critical level, you see a difference. No? Okay, energy. I'm talking about large resonance number flow, then energy impinge, wave carriage energy impinge on the critical level, okay, it's for large resonance number is absorbed. And you don't have a lot of them, okay, almost kind of, you don't see it here because a lot of energy is absorbed by the critical level. For smaller resonance number flow, you can have more reflection and some penetrate to the upper layer. Okay. Okay, again, for steady state flow, like steady state flow over mountain, then the critical level will be the same level as the wind reversal level. That's U become 0. Okay. Once your U, wind direction reversed, that level is critical level for steady state flow. Because as I said, that is steady state means partial t of any variable will be equal to 0. That means negative I omega of that variable equals 0. That means omega equals 0. Omega equals 0, that means omega divided by k is c. That's the phase speed equals to 0. And that means U equals to c equals 0. So wind, basic wind reverses, that's critical level for steady state flow. Okay. Remember that, okay. Okay, so here I have more further reading for you to read if you are interested, okay. You're interested because if you have rotation, you can add rotation into it, okay. And then you got very interesting because you have rotation into it, okay. And we see here, you see here, you see here, you see here. So look at downstairs here, the denominator. Look at here, denominator here. Okay. Look at this term, denominator here. How many singularities? How many? Singularity. U equals to C is 1. This one and this one, 2 more. So when you have critical level, when you have rotation, you have 3 critical levels. And this one is the same as before, because if F equals 0, this term is gone. You only have F equals 0. You only have 1 critical level. Okay. But when you have the rotation, you got 2 more. And this one is called classical critical level. These 2 are called Rossby critical level. Okay. Rossby critical level. And so there are some scientists, they work on this kind of problem. Like Utere, okay, he's working on this too. And Jones also, different people have different names, okay. Jones in 1967, he also established theories with rotation. And he called them inertial critical levels. I have a former student, Shen. Have you heard of Sun Bowen? Sun Bowen? No? Okay, so too young. Okay, he graduated from here, undergraduate and master's. And then he went to do PhD with me at the North Carolina State University. Okay, so we also have a theory, okay, starting this kind of flow, okay, with kind of inertial, with the Rossby critical levels. Okay, so then let me see what else. Okay, that's it for this. For this chapter. Okay, for this chapter.
Can we go back to the 3.4? It's 3.834.
3.8.
3.8.4.
0.4. No, no, it's just to save writing. Okay.
And you mentioned about
We just, but one thing important is I purposely reverse it because normally for this number greater than quarter, so this will be positive. Okay, that's okay.
So you mean if the number is greater than quarter?
Yeah, normally you want to. Yeah, normally you this kind of problem you don't want to solve for less than quarter because less than quarter is unstable case.
Unstable means
Linear theory doesn't work. Yeah. Okay, you don't want to deal with that because so when you have instability like you bring the core air, okay, on top of the warm air, then it's going to overturn in. Once you overturn in, your instability released, and then linear theory doesn't work. So that's why we assume that. Okay. Then you have turbulence, yeah, and you have mixing. Okay, any other questions? Okay, if not, I think let's take a break for 10 minutes. Okay, and then probably we can work on the project one. Okay, yeah, I explain a little bit, and your questions you ask, and then you can probably just do it. Okay, and then okay, I don't anticipate you will get it done. Okay, in class, but okay, your questions we can discuss, and then you can go home, finish it, and also make sure you know how to do plotting. Okay, I challenged to pass you a kind of PowerPoint of the grades. How many of you have plotted using computers? How many of you? Probably pretty much everybody, right? Have you done plotting using computer? Which kind of language software do you use? Great? Yeah, that's good. That's good. Okay, that's good. So what you use grades, right? Yeah. NCL. Oh, you can use NCL. Yeah, yeah. NCL is a good language. Yeah, yeah. It's a good plotting routine. Yeah, yeah. Okay. When I done the plotting, I done the Enka graphics, and that's before NCL because then that developed, and then NCL is Enka, okay, control language, Enka graphics control language. That's NCL. So when we do plotting, we have Fortran program. We go in, we change things, okay, and then later on develop. So people kind of develop, and then okay, develop your script. So then you just change the script, okay, and for model you just change the how do you call it? The name list, okay, name list. And for plotting, you just change the NCL, okay. No, you just change the script. So then people do scripting, okay. And when I did plotting, we never have that. That's a new word called scripting. Okay. Anyway, we will try to discuss that. Okay. And then tomorrow morning we'll start to talk about the wave generation and maintenance. And it probably will take not long. So then after that, we'll start to talk about mountain waves. Okay. Let's take a break. So you can also download Grace tutorial if you're not familiar with. But I believe you guys are probably familiar with, okay, Grace. If not, you can use any other type of plotting subroutine. Okay, and you can modify the Fortran code of the shallow water model so you can output to the format you need it. Okay. I believe you guys are familiar, right? No? Yeah, okay. You probably don't want to read this one. Try to read that project one, the model, shallow water model. Shallow water model, try to download shallow water model and try to read it. And to see how much you understand it, and you, okay, what we need to do is try to run it, plot it, and find at least three regimes. you probably need to work on that to look at do it that Fortran program first. Yeah. Oh, here, this one. Yeah. Yeah, AutoPad. Yeah, AutoPad should be good. Yeah. Okay. And can you also, I don't know, you probably want to post on the video if they need the Fortran program. Okay. Tell them probably to email me so I can forward that to them. Okay, if they need the Fortran program, this program. We call shallow water model for project 1. Okay. Do you know how to post? Okay, announce it, make announcement. Announcement.
Right on the YouTube, the live, right now it's the M1 video.
Yeah. Tell them we are doing the lab, okay, project 1. If they need a project 1, they need the Fortran program. Okay, tell them to, you guys, yeah. So you can just forward that to them, okay. So tell them we are doing the project 1. And if they need the project 1, and also the shallow water model, okay, let us know, yeah, okay, that means you, okay, you can forward to them. Okay, so basically this shallow water model is based on that the 2 equations we have in the class. Okay, if you go back to your note, okay, we have the, let me see, we have, maybe I can write down for you. I believe you have probably in your note. We have this the model solve these 2 equations. Okay, solve these two equations. So this one, solve, this is 3.4.6. This is solve u prime. Okay, this is solve h prime. Okay. And how many of you have taken the enthalpy or numerical modeling class? You have? Yeah. Homework, okay. Yeah. But probably you don't have to worry too much about the inside. But try to learn how to do it, how to, maybe Chao, you can explain a little bit of this to them. Yeah.
So the code and
Probably how to do it, because some of them probably don't have the background to understand the model, but how to do it, okay. So, so those are name list you need, okay. NT, okay, dt, that's delta t, the time interval. And NT is how many times for integration, okay. And then MPR, that's for the number of printout, okay. Because you don't want to print out every time step, that's too much data. And then dx, that's the grid point, grid interval. And then NL, that's NL means nonlinear. When it's nonlinear, okay, and NL equals 0 is linear. Okay, UP is a basic wind speed, like for example 10 meters per second, for example. And HB, that's the basic the height, undisturbed height, capital H. That's capital H. Okay. So this is called HB. This one is called UB. Okay. And then you set the, basically you probably don't need to change anything right now, okay, because it's already set up, okay, it's already set up. Like here, U naught equals 0, okay, and then H naught is equals to 0, okay, that's, U naught is this initial perturbation, okay, and H naught. And then, let me see, it'll be challenging because those are probably more complicated than what your background, some of you probably understand that, but if you don't, at least you probably can try to run the model. Okay, so start with integration. T, that's time, times delta t. So then delta t is keep going, then eventually you run to certain time for the output you want. And this is MPRT, that's a number of printout time, okay. And update. So Chao, do you feel comfortable to explain this to them? To run it. This is just similar to what you did before. Do you remember that? This is project. Let's probably listen to what questions they may have. Okay, How many of you have done some modeling before? Modeling, wolf, or any kind of modeling? Raise your hand. You too, right? 1, 2, 3. Only 3? How many? 4?
And also they have already.
Oh, yeah?
Yeah.
Oh, okay. So why don't you go to your group,
Yeah.
okay, and then try to learn it, okay? Try to understand first. And your questions you can ask me or Chia Hong, okay? Yeah. And do you have the group? Go to your group, okay? Yeah.